This is the Google Earth Engine. There are they provide time lapse. They use the historical remote sensing dataset to generate any spatial specific location. So you can, for example, we can select San Francisco area. It's very easy to give us a general idea of how this area, the land cover changed, or some human activity changed. Next one is the dataset on Google Earth Engine. Google Earth Engine provides different sources, remote sensing dataset, like the most popular Landsat data, including Landsat 5, 4, 7, 8, and also the latest launched Sentinel data. It's a European Space Agency dataset, including Sentinel-1 and Sentinel-2. Also modest dataset, more than 10 years observations. So our NEX-DCP30 dataset in here, this category, climate and weather. You will see at climate search dataset. The first one is NASA Earth Exchange downscaled DCP30 dataset. We will use this dataset for our hands-on exercise. So Google Earth Engine provides a pretty good document for the users to get into. For example, there is a documentation. You can find almost any documentation, documents and sample codes. So it's easy for user to get on to start their studies. And most important is the code editor. We will use this code editor to conduct all our spatial analysis. So, for example, we will first to check our DCP30 data set on Google Earth Engine. This code editor is a IDE environment. They provide a script panel. You can save your script and share your script to the other users. Also, you can upload your dataset from here, upload your raster dataset and the vector dataset. The central panel is a code editor. We can write our code and run here. And then we get a result from this console. And also we have some tasks, for example, to export your dataset or upload your dataset. So here we run our first. See, here we define, by using JavaScript, we define a variable NEX-DCP30. We are using EE.image. We always use EE, which means Earth Engine object. But you keep in mind, it's not a real object, it's a practical object. Every time you start from EE, which means the server will reinterpret this object to the JSON object. We use dataset, use this variable to load our dataset, and then we first need to filter the dataset. For example, we use different scenarios. Here we use RCP85. We also can use filter the metadata. For example, here we are using the model equals CC SM4. And then after we run the dataset, we can see our data is over here. There are more than 1,000 image layers, and in each image layer, there are 3 different bands. So like see, First one is precipitation, and then monthly minimum temperature, maximum temperature. All the images DCP30 are saved like this. This is we generate a small image cube by using this image collection. So on Google Earth Engine, when you're working with your raster dataset, there are two concepts we need to know. First one is image collection. Image collection means there are the same images, they put them together so that you can easily to pull them out and filter the dataset. And then next one is ee.image. That means you can directly access an individual image file, and then to get your you want the band to conduct your calculation. So use this print, we print out the properties of this dataset. For example, we will know the property of the tags, the title of this dataset. This gives us a general idea of DCP30 on Google Earth Engine. And then we will go ahead to try to find more information about our DCP30 on Google Earth Engine. We can try to find the date, the data range. See, we can print out the data range, and then we can also export to a list to get for the further analysis. We also can print out this small image collection. How many elements, and also the other information about this dataset. This block gives us a method to access individual image. You can see we print out our filtered dataset. This is an image collection, right? There are more than 1,000 layers, and this is each individual layer. Each layer including 3 bands. For here, we have another method to directly access individual images by giving the dataset name, the image collection name, and the image file name. We can directly access the data, and we can also load the data to Google Earth Engine to see what it looks like. See, we are using a map and a layer to enter the data in onto Google Earth Engine. So here we use define a visualization parameter. So we define which band should be used for the map, and also we define the minimum and maximum value for this dataset. Also, we can define a color plate.
Is there a particular line in this code that restricts it? Because it seems like you only visualize in the US right now. Is it a whole global data set, or is the data now only the United States?
For this DCP30 dataset, it's only continental United States.
Okay.
But we also have the other dataset, GDP30. Oh no, sorry. GDP dataset, that's global dataset. Also on Google Earth Engine, you can, for that GDP dataset, you can very easy to just define a small area. We only load this area, and if we want to just conduct analysis by using this dataset, we will show you later. Yeah. Next, on this block, we define a reference, and then we reduce. Do you remember the reducer? We reduce the data set, a small collection, and then we use the reducer over here. Okay, we use this reducer to generate a median or maximum or mean value of each pixel across this long time series. For example, here we select 10-year dataset, right? From 2011 to 2020, and then we use this reduce, just like here. We use the reducer from this long time series dataset to calculate just one layer. This one layer represents, for example, maybe it's mean or median or maximum value of all these pixels, this pixel by pixel calculation. If we run this code, we will see for each layer, we generate a median. This is good, you know, when you're loading the global Landsat data or the other global remote sensing data, most of the times we want to load the cloud-free dataset, right? But, you know, for traditional remote sensing software, it's hard to do that because you cannot load 10 years or 30 years dataset together and then to get each pixel value, the proper value, cloud-free. It's hard. But on Google's engine, it's pretty easy. Just a very small code block, you can generate a median. Median means across these 10 years, for each image band, each image band, we will get the median of these pixel values. For get the median means you have a good chance to get a cloud-free pixel. It's pretty smart and easy. So here, we just use this one block to generate, for each band we generate its median. Next one, we can load this dataset. Load this, generate the new layer. For load the dataset, we use the first one, map center object, median, which means we use this dataset to center the display. And then we define how to display the dataset on Google Earth Engine. It's, you know, compared to our desktop GIS software, it's a little bit complicated, but it's, once you familiar with that, it will be interesting. So you may notice that so for each pixel, it's when you load in this lower scale, it's pretty easy. Just instantly you get the data result. But when you load, when you zoom in, you will find it's a little bit smaller, right? This is another you know, character from Google Earth Engine. Google Earth Engine uses the dataset for the calculator on the fly. It's not pre-calculated. It's when you zoom in, you immediately get the calculation. There is a cluster, more than 1,000 CPUs are working with that. Google Earth Engine smartly to automatically split this image or this area split to small pixel areas and then spread to different CPUs to calculation and then return the result. So this is the first exercise, give us a general idea of DCP30 dataset on Google Earth Engine, and we will know how to load the dataset, how to get the proper layers we wanted, and how to get a simple calculation like a median, mean. So next one, we will have Google DCP30 data for time series analysis and spatial analysis on Google Earth Engine. So first, let's load the dataset again. We loaded this dataset. We only use 1 year, see from 2011, 1 year dataset. It's easier for us to get the result. And then we filter the data, only use one green gas emission scenario, RCP80 file, and use only one model. You know, for here, every dataset we have different models, but here we only use this one model to do dataset. And then we use further selection or further reducer to select only one dataset only including the temperature and the other only including the precipitation. So we can select only the bands, maximum and minimum temperature, and another band is precipitation. So once we run this dataset, we will know the first printout is 12 elements, right? Monthly dataset. And each month we have, this is temperature. We have only 2 bands, maximum and minimum temperature. We also can get the precipitation. We're using this new code block to generate, first we generate a small area. We define a geometry. It's a small area. We define actually it's a point, and then we buffer it so that we will get a circle. We define this area, and then we can load this small area on the map, display it on the map, and then we generate a time series chart. So here we can first to check the result. This is a point just above our head. It's NASA Ames Center, our building 19. We generate 12 months temperature change. This is a time series analysis. You can see we are using this 1 year dataset, and then we use this small area geometry small area. We use the image series it's provided by Google Earth Engine to conduct a time series value extraction. So here we use reducer to calculate the mean value, which means for each month we get the mean value, and then we are using another. This is skew. We talked about it before. You know, the skew is very important. The skew means we are not using the raw pixel value to generate our result. We then use this small option section to define how to show this chart. And then after we get the result, we can print it out. It's like this one. You can get here. It's a PNG picture. This is a simple time series analysis by using GDP30 over a point or over a small area. Next, we will define a polygon area. Actually, here we define 3 different areas. One is the urban area, city, forest, and desert. We define these 3 polygons, and then we calculate these 3 polygon areas 12 months temperature change, and then we print out the result. So from the map here, we can see this small area is San Francisco City, and then next one it's Sierra Nevada forest, and then it's a desert area. Okay, for different land cover, city, forest, desert, we will have this time series trend. You can export this trend out to go further for the spatial time series analysis. For example, you want to get each local the time trend next